Speech data contains various types of idiosyncratic information about speakers, which can be revealed by human listeners or by automated systems. This information includes, among other things, speaker identity, age, gender, ethnic origin, health, or emotional state. In recent years, there has been growing interest in privacy preservation solutions for speech technology. To promote the development of privacy preservation techniques for speech, the VoicePrivacy initiative was introduced, which focused on the voice anonymization procedures and tasks. The goal of voice anonymization is to suppress personally identifiable information within the speech signal, while maintaining all other characteristics. In particular, preserving the linguistic content of anonymized speech data and speech naturalists is essential. Before data processing and publication, speakers apply an anonymization method to their utterances in order to hide their identity. Different methods have been developed as outlined here. Ideally, anonymized utterances should sound as if they were produced by another speaker, which may be an artificial voice not belonging to an existing speaker. To evaluate the effectiveness of an anonymization algorithm, various subjective and objective methods have been proposed. Evaluation methodologies depend on the privacy preservation scenarios. In this work, we focused on subjective evaluation and considered the scenario of an attacker attempting to access a set of original and anonymized utterances from multiple speakers. Our goal was to examine performance accuracy when evaluators were tasked to link natural and anonymized speech recordings. By comparing the performance of human evaluators who assess natural and anonymized speech recordings between different systems, we might gain insight as to whether they were able to link or group similar speakers. By doing so, we might assess whether one system was more or less effective at suppressing identifiable speech characteristics. A separate goal was to assess correlations between subjective performance metrics and objective scores that represented the likelihood that the group speech recordings belonged to the same speaker. Speech recordings were selected from the VCTK corpus, which is composed of speech recordings read by over 700 native English speakers. 15 female and 15 male speakers were selected and divided into reference and distractor groups. 24 utterances were selected and reduced to a maximum duration of 3 seconds. 2 anonymization systems were considered baselines for the voice privacy challenge, which were used in this study. The B1 anonymization system uses X vectors and neural waveform models to synthesize anonymized speech. Its development required 3 steps. First, speaker X vectors, pitch, and linguistic features were extracted from the speech signal. Then, X vector anonymization was performed, where the original speaker X vector was replaced by a new anonymized X vector. Finally, the original linguistic features, pitch, and anonymized X vectors were used to synthesize anonymized speech by means of neural acoustic and waveform models. More details on the B1 development are available in the papers cited on this slide. The B2 anonymization system is based upon signal processing techniques. In contrast to the B1 system, it does not require any training data and is based on vocal tract filter transformations. The B2 anonymization algorithm is applied on the frame level and exploits the McAdams coefficient to perform anonymization by shifting the pole positions derived from the linear predictive coding analysis of speech signals. For more details on our development, please refer to the papers cited on this slide. The following demonstrates the timbral differences between systems. First, we present the natural speech recording.
Please call Stella.
Next, speech anonymization processed by the B1 anonymization system.
Please call Stella.
And finally, speech anonymization processed by the B2 anonymization system.
Please call Stella.
74 evaluators participated in our study. 26 identified as female and 48 as male. 29 were native English speakers. All non-native English-speaking evaluators were either bilingual or held a high level of English. The 39 Francophone evaluators represented the majority. Evaluators were tasked to listen to speech recordings and group them into clusters according to their perceived similarities. To do this, they used a custom interface developed at the Laboratoire Informatique d'Avignon. As seen here, the interface was accessible from a standard web browser. Throughout the testing, evaluators were provided instructions and were encouraged to use personal headphones. Each trial was composed of 16 different chunks, spoken by 3 different reference speakers and 1 distractor. The reference speakers were assigned between 2 and 6 different chunks. 1 control trial was composed of only natural speech recordings. 2 evaluation trials were composed of 8 anonymized chunks by reference and distractor speakers. All anonymized chunks were processed by the same baseline system. There are several methods used to evaluate clustering performance. This slide outlines the general evaluation scheme developed in our study. 1. Stimuli are selected for an evaluation trial. 2. Stimuli are randomly distributed on the interface. 3. An evaluator arranges the stimuli into different clusters. And 4. For each cluster, a principal speaker is identified. For 4, we identified 2 principal ways to identify the cluster centroid, or the proto-speaker of a cluster. For the first method, we identified the mode speaker in a cluster as the proto-speaker, which permits the possibility of multiple clusters being linked to the same speaker. For each cluster, we calculated the macro average F measure, which evaluates both precision and recall. For each cluster, we identified the number of true and false positives followed by the number of false negatives in the trial, and calculated the F1 as described in the slide. As an alternative method, we proposed the cluster purity metric, which identifies a different speaker to each cluster in a trial, as defined in the slide. Unlike F1, purity focuses only on maximizing the total number of true positive responses per cluster. Purity values range from 0 to 1, with 1 being perfect clustering. In addition to these metrics, we evaluated the mean speech recording listens per cluster, or listening count, as a way of assessing whether other performance factors were affected by the presence of anonymized speech. To compare subjective evaluation metrics, we use an ASV system that relies on X-vector speaker embeddings and probabilistic linear discriminant analysis. The ASV system was trained on the LibreSpeech dataset. The ASV model was used to obtain PLDA scores for evaluating pairs of speech segments. As defined in the slide, the PLDA scores were computed as log likelihood ratio values between corresponding X-vectors. For more information, please see the cited papers listed on the slide. To examine the effect of anonymized speech, for each evaluator, we calculated a difference between their performance during the control trial and their mean performance during the evaluation trials. Mixed ANOVA procedures were applied with anonymization system and language as between subject factors. Our results are illustrated in the table. For mean F1 difference, we found a main effect for language, but no other effects on system. Post-hoc t-tests showed non-native English-speaking evaluators were more affected by linking natural and anonymized speech recordings than native English-speaking evaluators by approximately 7%. This result is illustrated in the figure. We found no significant main effects or interactions on neither mean purity difference nor mean listening count difference. For the evaluation trials, Pearson correlation procedures were applied between PLDA log likelihood scores and mean F1, mean purity, and mean listening count metrics between systems and native and non-native English-speaking evaluators. The table illustrates our row coefficients and p-values. As we can see from the figure, there is a strong and significant correlation between objective and F1 metrics for the B2 system, but this is not the case for the B1 system. This study demonstrated that evaluators were able to use a clustering interface to link natural and anonymized speech recordings based on their perceived similarities. We reported no significant differences between systems across its objective metrics. However, we observed a significant difference between native and non-native English-speaking evaluators for mean F1 difference between control and evaluation trials. The significant correlations between subjective and objective results for B2 evaluation trials suggest evaluators clustered natural and anonymized speech recordings in a manner that was similar to the scores generated by our ASV model. The increase in the mean log likelihood scores between natural and B2 anonymized speech recordings correlated to an increase in subjective performance metrics. These observations were not consistent with the B1 system, which suggests that the evaluator performance was unaffected and independent of the mean log likelihood scores between speech recordings in a cluster. Regarding the general goals of voice privacy preservation, our findings suggest that the B1 system is more effective at encumbering any attacker trying to access a private database. We reported similar significant correlations for both native and non-native English-speaking evaluators between accuracy metrics and PLDA scores, which suggests spoken language familiarity did not affect performance when linking natural and anonymized speech recordings. Our findings add to the growing number of studies focused on voice privacy and anonymization. However, there remains many areas to develop. One critique of our study was the testing conditions, as evaluators were completely autonomous. While this mimics real-world environments, it was difficult to assess evaluator-specific factors, ranging from their understanding of the task to technical issues such as headphone use and internet connection. These factors might have influenced the performance of some evaluators, which underscore concerns regarding the current shift towards online perceptive studies. Speaker recognition algorithms are designed to train and test on hours of speech recordings derived from hundreds of speakers. As we were limited to 33 and 39 evaluators for the B1 and B2 anonymization systems, we were unable to examine any patterns associated with specific speakers. We might consider selecting a smaller set of male and female reference and distractor speakers so as to identify whether evaluators found the linking of natural and anonymized speech recordings belonging to certain speakers more or less difficult. This selection process could be done by conducting preliminary speaker comparisons based on PLDA scores and assembling different speaker groups based on measured similarities. We selected anonymized speech recordings from 2 anonymization algorithms. However, additional systems have been developed as part of the VoicePrivacy challenge. We aim to test these systems using similar methods to examine the limitations of linking natural and anonymized speech recordings. Thank you again, and we look forward to responding to your questions and comments.